welcome to Analytic number theory. In this video we are going to discuss theorem 9.1 of analytic number theory, text by Apostle. The theorem says that, theorem 9.1 says that if P is an odd prime number, then every residue, then every reduced residue system mode P, then every reduced residue system mode P contains exactly P minus 1 by 2 quadratic residues and exactly P minus 1 by 2 quadratic non-residues mode P. See, this theorem tells clearly about the total number of, or it tells us about the quadratic residues and quadratic non-residues corresponding to the given odd prime number P. The quadratic residues belong to, moreover, the theorem tells that the quadratic residues belong to the residue class containing the numbers. Quadratic residue belongs to the quadratic residue belongs to the residue class containing the numbers 1 square, 2 square, 3 square, etc. up to P minus 1 by 2 the whole square. So see, this list has connection with the selected prime number or the prime number. So the last number, it is obtained by subtracting 1 from the prime number and then it is divided by 2. So if 13 is the number, if 13 is the selected prime number for P, then the number here is 6. 13 minus 1 divided by 2 is 6 here. And on the other hand, if the number is 11 selected, if P is equal to 11, then we have 5. The number here is 5. So by choosing that number, or by finding the remainder when these numbers are divided by, when the squares listed here are divided by the selected prime number P, then we get a very clear idea about the quadratic residues. And those numbers appearing there as the remainder, which are not appearing as those numbers which are not appearing as the remainder in this list, can be accepted as the quadratic non-residues. So coming to the proof of this statement, initially we want to we put forward an argument that in this list, we have the list here which is named 2. In the list number 2 here, we have a set of squares. When these set of squares are divided by the number the number P, when these numbers are divided by the number P, we get remainders. These remainders will all be different. First we are going to show that our claim is that, initially our claim is that when we divide these numbers, when we divide all these numbers by the prime number P, you are going to get different remainders, and none of the remainders will be same. So in order to show this statement, in order to prove the claim, we initially we accept that, we very loosely we accept that, or we just assume that when we divide these numbers by the prime number P, we get two remainders the same. Or we just suppose that when we divide the numbers by the prime number P, then we get the same remainder. That can be taken, that can be written in symbolic form, in mathematical expression. As mathematical expression, you can write that when the number x square, see, you are considering two numbers here in the list. So first you write it is x square. When x square is divided by P, we get m as the remainder, and then another number y square, a different number, see, and its square, y square, when it is divided by P, you get the same remainder. So we are assuming that the remainders are same, so you have to take the same number m here in both cases, and then using this, so this is number 1 and number 2 numbered, and then and also you can see that as according to our the list selected, according to the a number is selected in the list, you know that the number is the continuously the natural numbers starting from 1 up to p minus 1 by 2 are written in this list, and their squares are written in the list. So the numbers are from 1 to p minus 1 by 2. Therefore you can say that whatever is the numbers selected for x and y, you are selecting for x and y two numbers from here. Okay, and therefore for that selection you can write this condition that 1 is always, because the starting number is 1 and the ending number is p minus 1 by 2, the maximum number is p minus 1 by 2. So always 1 is less than or equal to x or y. Both numbers satisfy this condition, x comma y less than or equal to p minus 1 by 2. And also you know that since we select two different numbers from this list, you can also say that x is not equal to y in this situation. Okay, then what we do, we are going to subtract this number, either this is subtracted from this or that one, the second one is subtracted from the first. See here, second one is subtracted from the first. Then this is, it's not ordinary subtraction, but the congruent subtraction of two congruent expressions is done here. So you have to follow the rules of subtraction of congruence to congruent equations. What way you have to subtract the two congruent equations, that you have to follow that rule, you have to follow here. Then using that, you can get that x square minus y square, that is the difference of left hand side, x square minus y square is then congruent to 0 mod p. Okay, that you can, for that you can refer the previous results. X square minus y square is congruent to 0 mod p. Then the left hand side, in the next step you can split the left hand side and write that x minus y into x plus y is congruent to 0 mod p, right? Okay, what does it mean? It means that the last statement, and this line states that, or this expression says that the product x minus y into x plus y can be divided by p, and since p is a prime number, and p must either divide x minus y or divide x plus y. So that is the last that is the last point that we can conclude here from this last step. Okay, and then and that is written here. So this implies that p divides either x minus y or p divides x plus y. Let's now think about both situations separately, and now we are going to say that considering these two situations separately, we are going to say that both these, neither the first situation nor the second situation is going to happen. Here we have either first situation or second situation to happen. We are standing at the conclusion. We are standing with the conclusion that either the first statement or the second statement must be true. But by considering separately these two statements, we will show that neither the first statement nor the second statement can happen. That means we are going to get a contradiction. So we are slowly we are going to obtain a contradiction. We are going to develop a contradiction, and using that contradiction, at the point of at the point when we get the contradiction, then you have to correct the previous step that we have very carelessly taken. Okay, then considering the first thing, see, let's think about p divides x minus y. You know that x and y, these two numbers satisfy this this inequality, 1 less than or equal to x or both x and y less than or equal to p minus 1 by 2. So then when we when we subtract one of these numbers from the other number, then you are going to get a number which is very less than p minus 1 by 2, very clearly which is less than p minus 1 by 2. That means you are not going to get a number which is greater than p. You are either p or some number greater than p. That's very clear. So so for that what then we can conclude about this from this point. What we can conclude then, okay, since x minus y is less than p minus 1 by 2, this is very strict. This fact is very strict, and then therefore p cannot divide. Since this quantity is less than p minus 1 by 2, you know that p cannot divide any number which is less than p minus 1, right? P only then 0. P can divide 0. P can divide some some number which is less than p, or only one number is there, that number is 0. So except 0, you can you know that p cannot divide any number, any other number which is less than p, but p can divide p, right? That's correct. So 0 is the first number and next number is p. In between these two numbers, p cannot divide none of the numbers. Okay. And therefore, due to this, but we are considering here the numbers from 1 up to p minus 1 by 2. Therefore, and also since we are finding the difference of the number x and x minus y or y minus x, any one of the difference we consider, and since that number is less than p minus 1 by 2, then p cannot divide. Due to that, our last point that we have been discussing, and we can conclude that p cannot divide x minus y. Okay, then we are going to consider the other statement. We are going to check whether p can divide x plus y. We also then for that we consider x plus y, but you can see that we want to find the maximum value possible that can be possible when you consider the two numbers x and y from this range. What will be that maximum value? We are going to consider, we are going to think about the maximum value you are going to get for the expression x plus y, for this expression x plus y, when we consider the numbers x and y in this range, from this range, and that value you will get that value only when both are equal to p minus 1 by 2. When you take x equal to p minus 1 by 2 and y equal to p minus 1 by 2, then only you are going to get the maximum value. So for obtaining that maximum value, then in that case, in that maximum value case, you are going to get which number, x plus y is equal to p minus 1. So that even that number is 1 less than the number p. So even that number is less than p by the number 1. So therefore what? So we cannot, we can say that, therefore we can conclude that p cannot divide x minus y, x plus y also. So in this case, in the second case, p cannot divide x plus y because the number x plus y is not going to be 0. In the previous case also, you can exclude the possibility of 0 because x minus y is not going to be 0 because we are considering x and y as two different numbers. Therefore, x minus y cannot be equal to 0. But in this case also, x plus y cannot be equal to 0 because both x and y are greater than 1. Therefore, it cannot be equal to 0. Therefore, then next possibility is that it must be p. The number must be x plus y must be p in order to say that the number x plus y is divisible by p, but that is not going to happen because the maximum value possible for x plus y is p minus 1. So due to these findings, you can say that p can neither divide x minus y and nor divide x plus y. Thus we get the contradiction. We get the clear contradiction that we were looking for, that contradiction for that statement, for the existence of this statement. Contradiction for what? And we are getting the contradiction for the statement that x minus y into x plus y is equal to 0 mod p. Okay, and therefore something might have gone wrong. We have taken some wrong step. What would be that? What could be that wrong step? The wrong step could be that the statement accepted that the number and these are same. That wrong statement could be the statement that x square is congruent to m mod p and y square is congruent to m mod p. That is the remainders can be same. The remainders can be same when x square and y square, when they are divided by p, the remainders can be same. That might be that wrong step. So we have to correct that. That means when we divide the numbers, any two numbers which belong to this list, we must get, we very strictly we get two distinct remainders. Then we are coming to the last part of the proof. In the last part, here, okay. Yeah, this is the beginning of the last part. Next we shall show that k square and p minus k square. See, k is the number, we choose this number k, which belong to the range 1 to p minus 1. So here we suppose that k is a number, or you can take k is equal to k in this range, k belong to the range 1 up to p minus 1 by 2, then also it is correct. So we consider the number, we consider a number k which belongs to the range that you can see here, the range 1 less than or equal to p minus 1 by 2, and this is the range in which k can belong. Okay, then we are going to show that you take its square, you square it, that is k square, and also you consider the subtracted quantity, the quantity k subtracted from the quantity which is obtained by subtracting k from p, that is p minus k, you also consider, and in square we consider. So you have to consider the number k which belong to that interval and which belong to that range, and the number p minus k, and square we consider. Then we are going to say, then we argue that when we divide these two squares by the number p, we get different remainders. Sorry, we get the same remainders. Here it is not the different remainder. We have to show that we get the same remainder. So when we divide k square and p minus k square by the number p, we are going to get the same remainder. For that, let's assume that when we divide k square by p, we get m as the remainder. You just assume that k square, when k square is divided by p, we get m as the remainder. Then we consider the other square, the other quantity, that is p minus k the whole square. Okay, and you know that when we expand it, we get that p square, it's equal to, it is not congruence, it's equal to p square minus 2pk when the exponent is expanded, 2pk minus 2pk plus k square. Okay, and then since these two quantities, when we examine these two quantities, the first two terms, you can see that contains the number p. Yeah, here it is p square and here it is p. So we can divide the first and the second quantity together by p, and therefore you can clearly write that p minus k the whole square is congruent to the last term. Last term can be written, and that is k square mod p. So you can write p minus k the whole square is congruent to k square mod p. And but you know considering this this assumption, this taken step, k square is congruent to m mod p, you can write that this k square is then when this k square is divided by p, we get that m as the remainder. So it is then further it is congruent to m mod p. And okay, and therefore we get that k square is congruent to m mod p, and p minus k the whole square is congruent to m mod p. Okay, thus we have completed that the proof of the theorem of the theorem number 9.1. And but we have to before closing that the video, we want to make some discussion on the effect of this result. That what is the main outcome of the result. It is that when you write the first part of the theorem says that when we divide these numbers up to p minus 1 by 2 the whole square, when we divide these numbers by the number p, you are going to get different remainders. And when you extend this list, in this list you cannot see the numbers, the other numbers up to p minus 1 square. Okay, so if you consider the remaining numbers, that is p minus 1 by 2 plus 1, next number is the square of the next number, that is p minus 1 by 2 plus 1 the whole square. Then next number is p minus 1 by 2 plus 2 the whole square, etc., up to what is the last number? The last number is p minus 1 the whole square, up to p minus 1 the whole square. So when you expand the list up to p minus 1 the whole square, then the remaining numbers can be divided by p, and you can examine that, you can check the remainder obtained. Then you can see that the remainders will be a repetition of the remainders that you are going to obtain from the first set of numbers, from the first list of numbers. Suppose you are going to get m as the remainder here, you are going to get m, the same remainder as the last remainder of the number. And if you are going to get n as the remainder from 2 square, you are going to get the same remainder as the second last remainder in the list, in the extended list. Okay, and that's the consequence of the last part of the result. Okay, this will help us to obtain the quadratic residues and quadratic non-residues of a given prime number. Okay, thank you.